Okay, I'm going to demonstrate how the real numbers can be counted. What this means is establishing a one-to-one correspondence between the real numbers and the natural numbers. Natural numbers are sometimes referred to as the counting numbers. They're numbers we use for counting objects like apples. 1, 2, 3, 4. The real numbers are all the natural numbers, the negative numbers, 0, any number that can be expressed with a decimal or a fraction, including decimals that continue forever, like pi or 0.333. Now it appears that there are more real numbers than there are natural numbers. So you might be thinking, how is it possible to count the real numbers? Well, there's an infinite number of real numbers, but there's also an infinite number of natural numbers. So no matter how long I go on counting the real numbers, I'll never run out of natural numbers to count them with. Since there are an infinite number of real numbers, I'm not actually going to count them all. But what I will do, as I mentioned earlier, is that I'm going to establish a one-to-one correspondence between the real numbers and the natural numbers. This is what we do when we count objects. When I counted the apples earlier, I assigned a number to each of the apples, 1, 2, 3, 4, establishing a one-to-one correspondence between the apples and the natural numbers. I didn't assign more than one number to an apple, 1, 2, 3, 4, 5, or more than one apple to a number, 1, 2, 2, 3. That wouldn't be counting. This is what we mean when we say counting is establishing a one-to-one correspondence with the natural numbers. If we can establish this one-to-one correspondence, we say objects are countable. So I could count all those apples, I could count all the apples in a tree, I could count all the stars in the sky. They're all countable. If there's an infinite quantity of something, and I can still establish a one-to-one correspondence between the natural numbers and those objects, we say those objects are infinitely countable. So, for example, the integers are countable if we draw a number line. Like this. 0, 1, 2, 3. Go a bit further. 4. -1, -2, -3. And I'll keep going. So the integers continue infinitely in the positive negative direction, but I can still count them by assigning a natural number to each of them in an alternating process. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. So the integers are infinitely countable. So that process can continue forever, but I can easily establish what natural number is assigned to any integer because there's a pattern here. Each positive integer is assigned an even natural number. 0 is assigned 1, and each negative integer is assigned an odd natural number. So if I wanted to know what natural number is assigned to 4, I just double it. 4 times 2 is 8, 3 times 2 is 6, and so on. And if I wanted to know which natural number is assigned to negative integers, I would multiply it by -2 and add 1. So -2 times -2 plus 1 is 5. -3 times -2 is 6 plus 1 is 7. So the real numbers are all the integers plus all the numbers between the integers. So, for example, 2.5 is halfway between 2 and 3. Negative 0.333 is 1/3 of the way between 0 and negative 1. Now, counting the real numbers is a bit more complicated. So instead of the number line, I'm going to use cones. This is just a way of demonstrating the process. So I'm going to start with the base of a cone, and I'm going to draw 10 points around the base. And I'm going to label them 0.0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. And then I'm going to draw the rest of the cone. And I'm going to label the apex 1. So then I'm going to draw a larger cone. And the base of this cone is going to represent 2 decimal places. So for every 1 decimal place, there are 10 possible 2 numbers in the second decimal place. So for example, starting with 0.0, I'm going to draw 10 lines just to keep track of things. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to draw one of the lines dashed for a reason I'll explain in a bit. And I'm going to label these ones with 2 decimal numbers. So this is going to be 0.00, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09. Now I can continue with this all the way around the circle. Oops, that should be slower lines. Okay, and then I'm going to draw the rest of this cone. And I'm going to label the apex 2. Then I'm going to draw a circle around this one. And in a similar way, I'm going to draw all the 1-digit numbers with an integral 1. So 1, the integral is the part before the decimal place. So all these have integral 0. Everything on this level is going to have integral 1. So again, I can have, draw one dotted line. this would be 1.0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, and 1.9. Okay, then I would repeat the process with an even bigger cone. So I'll draw a bigger base. And each of these lines would radiate out 10 lines of its own. And I'm going to draw one of them again with a dotted line. So the first circle had 10 points. The next circle had 100 points, 10 times 10, 10 to the power of 2. The next circle would have 1,000 points, 10 to the power of 3. If I drew all those lines, then I would complete this cone, label this 3, and then I would draw a circle, a wider circle around the numbers with integral 1. This would be all the 2 decimal numbers with integral 1. So there would be 100 of those. Then I would draw a circle around numbers with integral 2. So there would be 10 of those. And I continue this process indefinitely. So when we do this, you can see 2 things happen. We add another decimal place to each level, and we add another integral at the top. It increases by 1. So if we continued this diagram forever, we would have every integral component with any number of decimal places. So we'd have every possible positive real number. Now you notice I have only used the positive real numbers here. That's to simplify things. We could add 0 and all the negative real numbers as well by drawing cones underneath that extend indefinitely, and using a similar alternating process as we did for the integers, where an even positive natural number would be assigned to every positive real number. 1 would be assigned to 0, and odd natural numbers would be assigned to all the negative real numbers. So how are we going to count these numbers? Well, first I'm going to explain why I have a dashed line in some places. So when you add a 0 to a decimal number at the end, it doesn't really create a new number. So 2.50 is the same as 2.5. So I don't want to count any number that ends in a 0 after a decimal place, because I've already counted it. But 0 is an important placeholder if another number comes after it. So if I had 2.507, that wouldn't be the same as 2.57 if I just omitted the 0. So I want to keep track of the zeros, but I don't want to count them if they're at the end. I only want to count them if there's another number that eventually follows it. So when I count these eventually, I'm going to omit all the ones that end in a 0, and those are the ones that I have with the dashed line here. So all of the numbers that all the lines that are dashed lead to a number that is ending in a 0. So for example, this one is 0.10. This one is 0.30. Okay, so I'm going to erase this. Okay, now I'm going to draw table here, count these numbers. I'm going to put the integral component down the left side. And I'm going to put the number of decimal places along the top. So 0, 1, 2. So as you might be able to see from the diagram, there were 9 one-digit decimals of 0, excluding the number that ends in 0 after the decimal place. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to put that range in 1 decimal place, and then number 1 was our 10th real number. So I'm going to put the number 10 here. So number 1 with 0 decimal places. So I'm going to make columns here. So, 2-digit decimals with an integral 0, they started with 11, and there were 90 of those if you count them all, excluding the ones with dash lines that end in 0. So that would go to 11 to 100. The 1-digit decimals of 1, there would be 9 of those if you exclude 1.0, which has a 0 after the decimal place at the end. So that would be next number 101 to 109, and 2 was our 110th real number. Now, I'm going to draw another row here to label things. As you can see, there's only one number in this column. So there's, if you're just counting the integral components with 0 decimal places, there's only one number. So 1, 2, 3, and so on. Here, there are 9 1-digit decimals of each integral. So there's 9 in there. Here, there were 90 2-digit decimals. And this is going to continue. 900 in this one. It's going to be 9,000 numbers for each integral with 4 decimal places. And there's going to be 90,000 with 5 decimal places. So I'm just going to fill in a little bit more of this table. Okay, so this table would increase indefinitely, but we can see the pattern here that allows us to identify what real number corresponds with each natural number. So for example, if we just look at the integral components, 1 is the 10th number, 2 is the 110th number, 3 is the 1110th number. So you basically have 3 ones and a 0. For 4, you have 4 ones and a 0. For 5, you have 5 ones and a 0. And that will keep continuing. If you wanted to have the number 3.02, that is the second 2-digit decimal of 3. So it's the 3 integral component, 2 decimal places, and the range is this range here. Starts with 111011. So the second number in that range would be 111012. If you wanted to do a repeating or a infinite decimal like pi, let's say pi. So if you were just going to do the integral component, it would be 1110, so that would be the number assigned to it. If you wanted to be more accurate, it would be 3.1. So that would be the first 1-digit decimal of 3. So that'd be 11101. And you can make this as accurate as you want by adding decimal places to pi. Thanks for watching.